Welcome. On this video, we're going to be showing how can we use exponential and logarithm equations to properly model population growth and population decay. So let's get started. To illustrate that idea, we're going to take a look at this small introduction question, which states, suppose that the population of a small town, it grows at an annual rate of 2%. Now, if the current population of this town is of 10,000 residents, what is going to be the population in 5 years? So in order to answer that question, we're just going to create some kind of a table here. And let's understand what's going on here. So we're going to start with 10,000 people. And then once a year passes, the population is going to increase by 2%. So how do we calculate that increment? What we can do, we can get 10,000. So let me erase that. So 10,000. And we're going to multiply that times 0.02. But why 0.02? Because if we convert this percentage into decimals, that's equivalent to 0.02. So once we calculate this, what this is saying is that we're going to start with 10,000 people. And once we pass the first year, we're going to increase by 200 people, because that is 2% of 10,000. So now the population after 1 year is of 10,200. So now this is my new population. We started with 10,000 and then I just added 2%. Now we are at 10,200. So how are we going to calculate the year on the second, once the second year passes? Well, the same idea. We're going to get 10,200 and we're going to calculate 2% of that. So now we don't increase by 200, but now we're going to increase by 204 citizens or residents. So now my new population is of 10,404. So let's calculate now. What's going to be my population the third year? Well, again, how many citizens or residents are we going to add to it? Well, it's going to be 2% of the previous year. So now we're going to get 10,404, and we're going to multiply that to 0.02. So now we're going to increase by a total of 208.08 residents. But let's just be careful with this, because are we really adding 208.8 people or 0.08 people? This is not a whole person. This is a decimal of a person. But still, for the calculation, we're just going to add it by that decimal, even though it doesn't make a lot of sense to say, well, I'm going to add 0.08 of a person. So now if I add them up, now I'm going to have a total population of 10,612.8 residents. Let's find out what's the population on the fourth year. Again, I'm just going to add 2% of what the previous year was. So let's compute that. So 10,612.08. Sorry, I don't know why it keeps doing this L1 business. So let's start that one more time. So 10,612.08. So 0.08 times 0.02, we're going to get 212. So we're going to add 212 residents. So let's just write that down. So 212.2416. And then if we add them up, we're going to get a total population of 10,824.3216. And I'm not going to do that on the graphing calculator anymore because it's just taking too much time. So if we compute the 2% of that, that'll be 216.48. And that's going to give us a grand total of 11,040 points. So after 5 years, if the population keeps increasing by 2%, on the fifth year, we're going to get a grand total of 11,040.8 residents. Now let's answer the following questions and let's see if we can analyze what just happened here. So in the introduction problem, does there seem to be a pattern in our calculation? We know that there seems to be a pattern, and that pattern is of an exponential growth. Because what we did, so to find the new population, and by new population, I mean, let's say we wanted to find the first year, so we got 10,000, and then notice that what we did, we multiply times 0.02, and this is my new population. I multiply by 0.02, and this is my new population, and so forward. Notice that in order for me to find the new population, we multiply by 0.02 and added the result. Since we were multiplying 0.02 1, 2, 3, 4, 5 times, in this case, you can think about it as 0.02 to the fifth. This is pretty much what we did. We multiplied 0.02 to the fifth to find out the amount of times that the population increased. So notice that we have some kind of an exponential equation. 0.02 to the fifth, that's an exponential expression, I should say, not an equation. Now that we have observed that, yes, this is some kind of an exponential problem, can we somehow just calculate the same result but just faster? Well, we do have an equation that can help us out for this task, and that is the exponential growth formula. So the exponential growth formula. What is the exponential growth formula? Well, we're going to write it as f of t equals PO times e to the RT. Well, let's pause for a second. Let's try to figure out what all this means. So PO is the initial amount. Or what sometimes we call it the principal. R is the rate that we increase by. T is the time in our calculation. And then F of t is the final amount over time. And this formula that we do have here, it can help us out to find the population that we started on the initial problem. But now we can just compute the final result faster because we got that information. So let's go back to the problem and let's compute the same, but now using our exponential growth formula. So let's do that. So we're going to use the equation f of t equals PO times ERT. But before we do anything with this formula, let's identify what do we know about this formula. PO, which is the initial amount. Do we know what the initial amount is? Definitely we do. We started with 10,000 residents. So let's just write that out in there. So in this case, PO has an amount of 10,000. Now, do we know the rate? Well, I know that the rate was increasing by 2%. So the rate is 2%, but we're going to use the decimal representation, which is 0.02. Do we know the time that we're interested on? Well, we want to see the population growth after 5 years. So in this case, t is equal to 5. Most of the time, t is going to be in years. But if we want to compute it over certain months, that's going to be indicated on the problem. But 99.9% of the time, we want to use t as a reference for time in years. And do we know the final product? Well, that's actually what we want to find out. So the final product, or the final residency, I shouldn't call it residency, but the final amount of residents after 5 years, that's what we're looking for, f of t. And now that we have all this, let's just plug it into the actual formula and let's calculate that. So f of t is equivalent to PO, which we know is 10,000, times E, which is the Euler number. And as an exponent, I'm going to have 0.02 times t, which is 5. And now what we do have here on the right-hand side, this is something that we can use our graphing calculator to find that amount. So let's do that. Let's get 10,000 and let's multiply times E. And as an exponent, you got to be careful here because I'm going to put one parenthesis. So now this pair of parentheses is put for 0.02, and I need to multiply that times 5. So I'm going to close this parenthesis to close down the 5, and I'm going to use another parenthesis to close out the Euler number. So here we have this pair of parentheses is for the 0.02. This parenthesis with this parenthesis is for the 5, and now this parenthesis closes out this parenthesis. And now that we press enter, notice that we have that the final population over 5 years is equal to 11,051.71, which is a pretty good estimation from what we got initially. Even though if we would just compute it manually, we got 11,040. Using our calculation, it's 11,051. They're pretty close to each other. Now, the reason why we have different results, even though we have the same information here, is that when we were using our table of values, notice that we were using the whole decimals. So this is going to give a better estimation of the population after 5 years. But when we use this formula, every time that we use an Euler number, we use an approximation. And that approximation over an exponent, it does going to have some difference on our final result. So that's the difference between, or that is why we have a different result here. But regardless, this is a pretty good estimation, and we can definitely use this information to categorize this as our final result. So what's better? Just compute it as a table or compute it as a formula? Well, if you have a few years, you can just do it using a table. But what if you want to compute the population after 30 years or 40 years? You definitely don't want to use a table for that. It will be just better to just go straight to the exponential growth formula. Now, under example 2, it says, in the same town as the introduction problem, how long would it take for the population to reach 82,000 citizens? So now this question is different than what we were asked initially. In this problem, initially we wanted to find out the population after a certain amount of years, which in this case were 5. But under example 2, we're actually being asked for the time because it says, how long would it take for the population to reach 82,000 citizens? So we are looking for time. But I know that I can still use my exponential growth formula. So f of t is equal to PO times E R of t. And let's just write down what we know. Do we know the final result? Well, I know that my final result should be of 82,000 citizens. So that way, f of t is equal to 82,000 citizens. Now, do we know the initial population? Well, the initial population, it says that is the same problem that we started with. So therefore, my initial population is of 10,000. My initial population is of 10,000. Do we know the rate? Since it is the same problem, then the rate is 0.2. And now, do we know the time? Well, the time is actually what we're looking for. So we have a formula, and we have a lot of knowns and just one unknown. So we can definitely just plug it in and then just work it out algebraically. So let's plug in what we know. So we have f of t, which is 82,000. So I'm going to just plug in the information that I know. Just notice that I'm missing a 0 here. Cool. Equals PO, which is 10,000, times E to the R, but I know that R is 0.02, times T, where T is what we're looking for. And now, if I plug in all my information into this formula, this is what I end up with. Notice that what I'm looking for is for time, which we do have it here. And time seems to be the exponent of the Euler number. And now this just becomes a question of, can we solve this exponential equation? And we can definitely do that. Notice that 10,000 is being multiplied. So in order to get rid of it, I can just divide. And that's going to give me a result of 8.2. So we got 8.2 equals e to the 0.02 times t. In order to solve for t, I need to get rid of the Euler number. Notice that I can accomplish that by raising both sides to the ln. So now I have ln of 8.2 equals ln of e to the 0.02 times t. Let me just erase what's on the right hand side here. And once we have raised both sides by ln, notice that ln has a base of e, so that way the e's will cancel out. So now I have that ln of 8.2 that's equal to 0.02 times t. And if we want to solve for time, that 0.02 is being multiplied, so I'm going to do the opposite. I'm going to divide by 0.02. So now I have an expression for the value of t. So the time is the ln of 8.2 divided by 0.02. And this is something that we can use our graphing calculator to find. So let's find the time now. So let me just erase everything here. So we're going to go ln of 8.2 divided by 0.02. So that means that it's going to take us approximately 105. So I'm just going to say t, it's approximately 105 years. So if we have a population of 10,000 and that population keeps increasing by 2%, it's going to hit 82,000 at approximately 1.5 years. The last example that we're going to be looking at is whenever we have situations of not growth but decay. So let's suppose that the population of a small town, now it is not increasing. So now notice that we're using the word decay. So now we know that over time, the population is going to go down. So we have a decay now. And now the decay is of 2%. So if the current population of the town is 20,000 residents, what is going to be the population in 5 years? So whenever we encounter population decay, we can still use the population growth formula times e to the rt, but there's going to be a small difference. And that small difference is that now my rate is going to be negative. Why is it negative? Because now we're not adding individuals into my calculation, but we are subtracting individuals on my calculation. But notice that it is essentially the same. It is the same formula that we have for population increase or population growth, but now when we're using population decay, the only difference is now we have a negative rate. Therefore, we just got to put a little negative in front of the r. But everything else is still the same. So let's try to answer this question now that we have established that now for a decay we have a negative rate. What information do we know about this? Well, I know that the rate is of 2%, which is 0.02. The current population is 20,000, so PO is equal to 20,000. And it's asking what will be the population after 5 years, so therefore my T is 5 years. In this case, f of t is what we're looking for, the final population. So now that we have all this, let's just plug it in and let's calculate this. So now we're going to say, well, f of t equals initial population, which is 20,000, times e to the negative 0.02 times 5. And again, we write f of t, but this is just saying the final result after the time, what we're looking for the time is 5. So this is the correct notation for it. And what it's on the right-hand side, this is definitely something that we can use a graphing calculator to find. So let's find that value. So we're going to start with 20,000 people. And now we're going to multiply that by e, but be careful now, because now we have negative 0.02. And now we're going to close that parenthesis for the rate. We're going to open a new parenthesis for the 5. We're going to close the parenthesis for the 5. And now we're going to close the parenthesis for the exponential. So this is saying that now we have approximately 18,096.75. So this is saying that after 5 years, we have approximately 18,096 residents. Now let's see if our calculation kind of like makes sense. Well, we started with 20,000 and my calculation is saying that my result should be of a lower value since we are looking at a decay. And yeah, 18,000 is definitely lower than 20,000. So that's one way for you to kind of like see if your result makes sense. So what we have discussed today is that we can use exponential growth and exponential decay. We can manipulate that information to come up with population decay and population growth formula, and we can use that formula to calculate the population growth and population decay over time. And with this, it concludes our lesson for exponentials and log applications dealing with population growth and population decay.